Okay, thanks for the introduction. I'm going to talk about reducing signature size of matrix code-based signature schemes. And this is a joint work with my co-authors, Ruben, Lars, and Simona. Okay, so let me start with what this paper is actually about. So, well, everything actually comes from this very simple idea of representing asymmetries. Okay, didn't show. Representing asymmetries as interpolation data. And with this simple idea, we apply it to maths and LTAC, these two code-based signature schemes. And we are able to reduce the response size by a large factor. And as a result, the signature size is also reduced by a large factor. Okay. Oh, I should say that because I'm much more familiar with the math part, so today I'm going to focus on the math part, and well, the AOTQ part is, well, takes more time to discuss, so I'll just not going to talk much about it. Okay, so the underlying problem in maths is the metric co-equivalence problem. It's defined like this. So given two dimension K linear codes, C0 and C1, where cowords are considered as m times n matrices, the problem asks to find m by n matrix A and n by n matrix B, such that C1 is equal to A times 0 times B. Okay, so this is a very simple problem. And in my talk, well, I'll refer to this kind of map induced by A and B by asymmetry. Well, some people like to talk about group actions, but yeah, I'll just use asymmetry here. And if you wonder the relationship between M, N, and K, well, in the first version of the specification, we use, well, M equal to N equal to K. It's not like you cannot use unbalanced parameters, but well, that's what we have in the first version. Okay. So this is the underlying Sigma protocol in maths. So you have the prover is going to generate a random code C0 and generate a random asymmetry AB and send apply it to 0 to obtain the code C1. So now your C0 and C1 is going to be the public key, and the secret key is the asymmetry between them. And then prover generate another random asymmetry A tilde B tilde and apply it to C0 to get another code C prime. So this C prime is going to serve as your commitment. And the asymmetry A tilde B tilde, this is going to be the response when the challenge is 0. And when the challenge is 1, the assumption, the response is going to be this dash line, dash arrow. So this is a composition of the inverse of the secret key and the, well, and the A tilde B tilde. Okay. Okay, so this is a simple Sigma protocol. Verification also work very simply. The verifier just apply the response to either C0 or C1, depending on which challenge it is, and compare the result with the commitment. And as you can imagine, the Fisher-Shamir transform is applied to append the final signature scheme. And now you can see the response size is apparently n squared plus n squared field elements. Okay. Okay, now I can already talk about the main idea in our paper for maths. So the response is always going to be like an asymmetry between the code C0 or C1 and the commitment. Okay, and if you consider the individual code words, it's going to be something like this. So you have a C0 mapping to D0, some C1 mapping to D1. if you think about it, actually, most of the time, C0, C1, and there's only a unique asymmetry between this C0, C1 and D0, D1. So our idea is very simple. So how about we just represent the asymmetry with this interpolation data, C0, C1, and D0, D1. Okay, so this is the resulting sigma protocol if you really do this. So now to generate the commitment, the prover is going to generate C tilde 0, C tilde 1 in the code C0. And then it's also going to generate a random D0 and D1. That's going to lie in the commitment, although we don't know the commitment at this moment. And then to really derive the commitment, the prover will derive from the interpolation data and asymmetry, apply it to C0, and then really compute the commitment. Okay. And to represent the response, the prover just use 0, C1, D0, D1. Yeah, it's not going to use something like A, B. And similarly, for response for the challenge 1, yeah, D0, D1 are going to be the same, but C0, C1 are going to be the corresponding code words in the code C1. Okay, so this new sigma protocol is still very simple, but okay, the idea might look a bit silly because originally you have only 2 matrices. You only need 2 matrices to represent the asymmetry, and now we are increasing it to 4 matrices. So this looks like something stupid, but the funny thing is that this actually brings a lot of benefit. And why is that? This is because C0 and C1 only take 2K coordinates to represent. You can just use a coordinate corresponding to a basis of the C0 or C1. How about D0 and D1? Well, they can actually be considered as public data. So, well, you don't have to send anything. They take 0 bytes. Okay. And if you're not very comfortable about this, if you like to think about random D0 and D1, well, you can ask the prover to send 0, D1, but in order to save signature size, you can just send a seed that you can use to derive D0 and D1, and the seed can be very short. And you can actually use one seed to derive all the D0, D1 matrices in all the rounds when you apply the Fisher-Miller transform. Okay, so this variant is, well, of course, you still need to send the seed, but the seed is just a very small portion of the signature. Okay, so now everything looks fine, but I haven't talked about how you actually derive the asymmetry from C0, C1 and D0, D1. This can be difficult, right? But now I'm going to show it. Oh, another thing that I also didn't say why I have a n minus n smaller or equal to 1. That's also going to be explained here. So what you can do, the problem you're facing is like this. So you have D0 equal to AC0 B, and D1 equal to A C1 B. You want to solve this system for N and B. And if you consider entries in N and B as variables, then this looks like a quadratic system. But a simple thing you can do is to move B to the left-hand side, and then you suddenly have a linear system. And this is going to be a linear system with m squared plus n squared variables and 2 mn equations. Okay, so now the solution space is it depends on the relationship between m and n. So for example, if you have m equal to n, then this will lead to the number of equation will be equal to the number of variables, and most likely, eventually you will only get A equal to B inverse equal to 0, and of course this is not what we want. Okay, so the next case is when M and N differ in only 1. So in this case, the number of variables will be 1 more than the number of equations. And in this case, this will lead to a solution space like this, like alpha A times alpha inverse B. And although it seems that we have multiple solutions, but actually all these solutions, well, non-trivial solutions, will lead to the same isometry. Okay, so this is actually good. Yeah. And in the last case, if you have a number of variables that's greater than 1 more than equation. Oh, sorry, I should add an absolute value here. If the difference is more than 1, then this will lead to too many degrees of freedom. And what I mean by too many degrees of freedom is that, well, the prover can choose a solution from this bigger solution space, but you may have problems for the the verifier to agree on the same solution. So this will lead to actually incorrect, invalid sigma particle. Okay, so yeah, so now the only problem is like, so you see that there are many variables. Although it's a linear system, but there are many variables. So this means that, well, solving this linear system is still going to be kind of slow, like maybe it takes n to the 6 plus n to the 6, something like this. Actually, in our paper, we show like if you take T0 and D1 in a clever way, then okay, the cost is not too much. For example, if you consider n is equal to n plus 1, and you have a D0, which is identity matrix, well, concatenated with 0 column, and D1 is 0 column concatenated with identity matrix. And we show in the paper that, well, you have the resulting system is going to look like the picture on the left. And with some row operations, you can bring it to the picture on the right. And you can see that the system on the right is, well, it's almost in row echelon form. And the only thing that we need to deal with is the big M matrix on the bottom right. So reducing the original system to, well, reduce row echelon form boils down to reducing this much smaller matrix M. And reducing the matrix M, well, apparently takes only big O n to the 3, the operations. And well, of course, there are still other costs, like well, how you bring the system from the left to the right. And you also need to do some backward substitution. Well, all this cost is actually also big O n to the 3rd. Okay. So this is your overhead by using this new sigma particle. And if you consider the cost that we have to do in the original sigma particle, then well, like you have to, for example, apply the isometries to certain code, and also sometimes you need to reduce generator matrix of the commitment to reduce the row echelon form, and all these kind of operations are going to take a big O n to the 4th. So in some sense, the overhead is actually quite small compared to other costs. Okay, so this is well, some old and new parameter sets for maths, and the old ones are the ones with that in the category you can see a smaller sign. And the reason why we have this smaller sign is because, well, there's a new attack from Eurocrypt 2024. And this reduce the security of the old parameters. So our team proposed new parameters. And the thing you should notice is that for this new parameters, this n, m, and k are much larger. This is because we want to defend against the new attack. And also as the result, the public key size also increases for level 1 and level 3. As you can see, because the new Sigma protocol is so strong, so even with this increase of parameters, we still are able to achieve much smaller signature sizes. And how about AOT-EQ? Yeah, as you can see, the signature size, well, with a similar technique, we can also bring the signature size to about 1/3 of the original size. So the last thing I want to say is that for maths, well, I already explained that we're using this interpolation data to represent the asymmetries. So in some sense, the asymmetries are represented as cohorts and well, their corresponding images. The OTAC is harder to explain, but actually what we do is kind of like using partial cohorts, like incomplete cohorts to represent the asymmetries. So yeah, our papers are already online. So if you feel like knowing more about our work, for example, if you want to know more about the OTAC part, you can take a look. And this is all my talk. Thank you for listening.
Okay, we have time for the last question of the conference. Do we have any takers? No, then that will be me. So what would the running times be for these signatures? How do they compare to the other ones that are submitted to NIST?
So if you're talking about compared to other schemes, well, I actually don't remember that. I remember that if you just compare the result of using the original Sigma protocol and the new Sigma protocol, I think the speed are similar. I think the problem of math is like because of this Fisher-Shamir transform. So you always need to run lots of runs, and this is the main bottleneck of the performance. And to be honest, so far I don't think there's a very good way to solve this problem. I think eventually you just need to do something other than Fisher-Shamir transform, like maybe you change the whole construction totally, like maybe you use MPC in the head scheme. Yeah, something like that. Yeah.
Okay, thank you. Okay, very last question of the conference.
So I think there's another paper that also reduced the size of less,
Yes,
which is very
I think I'm in that paper. Yeah.
So what is the difference between the two papers, and like can you apply one technique to the other, and vice versa?
Yeah, I have to recall what I did before. So okay, if you're talking about like applying the idea of my today's talk to less, well, yeah, I have thought about that. In some condition of parameters, you can actually do that, but the result is not going to outperform our result for, I mean, the result in our last paper. Yeah. And the other way around, like using the technique in that paper and apply it to maths. Well, I have thought about it, but I haven't been able to achieve a good idea. So right now I haven't seen how to do this, but maybe there's a way to do this. Yeah, maybe. Yeah. Thank you.
Okay, let's thank Tung and the other speakers.